Okay. Okay, so let's start quickly. So again, welcome back to relativistic kinematics, which many of you are already using. So I believe that this will be more helpful to the beginners like first year and second year students. So let's ask the question, why rapidity? Because you see, we have slowly migrated from our known Cartesian coordinate system of x, y, z and other known observables or variables which we have been using in Newtonian dynamics dealing with any particle motion. And suddenly after MSc, when you join your PhD program, you find that our coordinate system has changed from x, y, z or px, py, pz, your momentum space, to now eta phi space, which is completely new to many people. And as you know, when you try to learn a new language, you will fumble with that. You will face lots of problems, and picturizing this or perceiving this in your mind will take little more time. Okay, so with this, let me motivate you. What is the reason of going to this domain of eta phi phase space, coming back from our Euclidean phase space? So for this, again, I remind you that this training of mind is very important. And we have slowly migrated from Newtonian dynamics of describing a single particle or a system of particles to this relativistic domain where special theory of relativity is a need. So I have introduced already the four vector concept, natural unit, and the Lorentz transformation equations. Okay, so now let's see. And also I explained you in my first class, the velocity cannot be used as a variable to describe this relativistic particles, because you cannot distinguish between 99% versus 99.99% of velocity of c. And Lorentz boost factor will be more important or useful to describe different particles in the relativistic domain. Fine. So let's go to a successive Lorentz boosts in the same direction. Okay. So this is represented by a single boost. Okay, where the transformation velocity can be written in this way. Okay, so the equations I have given for x and time, your x0 and x1, namely in our four vector notation component wise. So if you try to write a successive Lorentz transformation equations for velocity, you will find that this is nonlinear. Okay, so you can find that this is beta double prime is beta plus beta prime divided by 1 plus beta beta prime. Okay. And let's prove this to have a feeling. Otherwise, many people may be lost with this equation, because usually we have not performed this kind of, although we can do it, we have not realized this thing. Okay, so let's go to the proof. Let's assume that velocity v prime in L is observed as v double prime in L double prime. Okay, so I have two frame of references, namely L and L double prime. With respect to my laboratory, L is moving with velocity v prime with respect to the laboratory. L prime moves with v double prime. So now the question is, which way I will try to see L double prime with respect to laboratory. So it is like successive double Lorentz transformation. Okay, so the coordinates t prime x prime are expressed in terms of t and x1. Okay, so x1 is x essentially. So I may use back and forth x1 or x. So we understand that x1 is x, that is the boost direction, x direction. So using the usual Lorentz transformation equations, right? So let's omit the transverse directions which are not getting affected by Lorentz boost. So then I focus on my x0 and x1. So these are actually your x component or the boost direction component. Sorry, the x1 is the boost direction component and x0 is the time component. Perfectly all right. So we know already this transformation equations, right? Lorentz transformation equations I have wrote earlier. And if I calculate beta prime, which is equal to v prime by c, okay, beta is defined as the relative velocity of the particle or of the system with respect to the speed of light. So then this can be written as dx1 divided by dx0. So now, I use these same equations, and now I can prove that this beta double prime will be x dx1 prime divided by your dx0 prime, and then I put on this corresponding equations, and I saw that beta double prime is equal to beta plus beta prime divided by 1 plus beta beta prime. So you see the velocity is not an additive quantity. Okay, in successive Lorentz transformations, this behaves in a non-linear way. Okay, so that is why it is not very suitable. And the question is, can we have any other variable which can take the place of velocity, and we will have a relatively better description. At least you see, if you look at particle spectra, spectral invariance under Lorentz transformation will be something which everybody will like. Okay, and as you see, velocity of the particle, if I look into, since it is nonlinear, I will not have a spectral invariance of the particles. So shape invariance of the spectra of different particles. So that is why velocity is no longer a chosen variable in the relativistic domain, and this prompts me to define rapidity to circumvent this drawback. And I introduce a variable rapidity which is y, and this is related to the known relative velocity beta, and beta is nothing but tan hyperbolic y. So if beta is introduced, so this is essentially a definition. I should put 3 bars, 3 lines, okay, instead of equal to, because it's a definition. So beta is equal to tan hyperbolic y, and then I redefine or rewrite y in terms of beta as half of the natural log of 1 plus beta divided by 1 minus beta. Okay. So we can show that rapidity is an additive quantity in successive Lorentz transformation. Now I showed that beta is not additive, it is nonlinear. But if I make a transformation, okay, to rapidity, so I can show that under successive Lorentz transformations, so you will find it is additive. So can anybody show this? I think many of you have done it. So since this lecture particularly, I'm a little faster with my official engagements. So let me quickly show few things. So y double prime will be your original y plus y prime. So here it might happen that y or y prime can be the rapidity of the center of mass. Okay, so we'll come back to this, but let's get into the related mathematical issues and how we correlate with our known knowledge. That is important, right? When I started learning a new language like English from my mother tongue, more often I was translating in my mind, right? So this is the basic of any learning of new language, and that is also equally applicable to what we learn in new coordinate transformations and all that. Okay, so let me now relate to whatever you knew. Okay, so then this will not be a strange thing for you, or I am not throwing on you. Okay, so with this, let's see, using rapidity, a Lorentz transformation with finite y can be decomposed into n successive transformations with rapidity, simply dividing delta y as y divided by n. If there are n successive Lorentz transformations, the total transformation will be, your individual differential transformation will be y by n. Okay, so it's essentially, if you consider a rotation of an angle theta, so I can have a delta theta which is equal to theta divided by n. Okay, so you make successive rotations, okay, adding more angle and angle. So that is also equivalent to making successive transformation of delta y. Okay, so then as I explained you, I should correlate this y or delta y with the known transformation which usually we do a rotation around one axis. So if I show that, so then you will be convinced. Okay, so essentially it is a new language. So solving now beta and gamma in terms of y. Okay, so from this definition, so I can show that, you know, this is my definition, beta is equal to tan hyperbolic y. Then you use the properties of hyperbolic functions, and you can show that your gamma is cos hyperbolic y, beta gamma is sin hyperbolic y. So explicitly I have written beta gamma because I'll be using that, okay, for your energy, momentum, all these things. So that is why I need explicit relationships. So now Lorentz boost can now be written as, so this is essentially, I remind you about your rotations. So your x0 prime can be written as cos hyperbolic y, x0 plus sin hyperbolic y x1. Similarly, your x1 gets transformed using this sine and cos. Okay. So this is a known expression, and I think everybody should do it once, because with the time gap you will forget how it was done. And in fact, last year I took my pen and paper and tried to do myself, and I faced a little problem also while doing it, because it is out of practice kind of stuff. So you try to do it once so that that stays in your mind. And if you compare this rotation with the rotation of xy plane along around one axis, for example z axis, with an angle theta, so you'll find that your x prime was earlier written as x is equal to cos theta minus y sine theta. Y prime was it is essentially how after the rotation the new coordinates x prime and y prime are related to your x and y of the present coordinate system. So those will be related through your cos theta and sine theta. And how these equations are coming, at least I know everybody knows it, but let's do it once more so that you have a direct correspondence with this new coordinate system. So we can obtain the former equations by just substituting. If I substitute theta by minus iy, x by minus I x0, and y by x1, essentially I can get these equations. That means using Lorentz boost, when I introduced rapidity y, whatever transformation equations I showed you in the last slide, that is equivalent to making these changes and relating it to the known rotation around an axis. So this Lorentz boost in x direction is now formally a rotation by an angle minus iy in the plane x and imaginary time, which is I x0. Okay. So earlier we had x and y plane and the rotation was happening around z plane. So here what is happening is now your boost is along x direction, and you find this is equivalent to an angle rotation of minus iy, and the plane is x and ix0, which is your time and x, your boost direction x and your time, because these two are getting transformed. Yeah. So now what is the experimental consideration? So is it purely mathematical that the problem I faced with velocity, I can get rid of that by introducing y or the rapidity, or it is little more than that? So let's look into experimental considerations, because we are at the end of the day experimentalists. So in high energy collider experiments, if you see, your secondary particles, they are formed in the interaction point, or depending upon their lifetime, they decay, and around the interaction point is the right wording. And always the boost is along the z direction. Z direction is longitudinal direction or the beam direction. So the boosted angular distribution is better expressed in the rapidity distribution. And at high energies, we know my E goes like PC, or since I am considering longitudinal direction, my P parallel or P longitudinal is P cos theta. And its rapidity is approximated by pseudorapidity. So this is a mistake. So I could not change it because it was done in LaTeX. So this is essentially y. So y from my last definition was half log 1 plus beta parallel divided by 1 minus beta parallel. So now from this I can rewrite in using energy and momentum, and I can show that this is nothing but minus log tan theta by 2, right? So your E can be written as P parallel is equal to P cos theta, because E goes like PC, C is equal to 1, okay? And then I can take common P parallel or P cos theta, so then things will cancel out. So giving me minus log tan theta by 2. So at very high energies, so we can approximate rapidity with pseudorapidity, and the single variable is emerging out at the end of the day, which is your emission angle of the secondary particles from the collision point, that is theta. And if I have a detector somewhere, I exactly know the position of the particle. So then, so this will give me theta. So then I have a better handle on the tracking of the particles. So in fact, this is taken into account while designing the detectors, and which are divided into modules that span the same solid angle in the eta phi azimuthal plane. So maybe this statement is not exactly digestible directly. So let me picturize this. Okay. So once I picturize this, things will be better. So now you look at the interaction point is IP, this one. Z axis is your beam axis. Okay. So two beams are coming and colliding at the interaction point. So you can have detector all around the interaction point. Okay. And you know from our detector classes why and how detectors are chosen for a particular position Okay, why different detectors cannot be interchanged, for example, with calorimeter versus tracker and all that. So those things you know it. So now let me just say that something is a detector. So this is a detector. A particle is coming or emerging out with a angle theta. Okay, and this is striking at this point. So now you look at any detector plane. So you can put it here, crossing the interaction point, crossing the beam axis, or you can put somewhere perpendicular to that. Doesn't matter, because it is essentially emission of particles in all possible directions. So now the particle which is actually striking on my detector, this line makes an angle theta with the beam axis. So then the striking point, which corresponds to a particular theta, actually makes a pseudorapidity which is annular in shape. In the sense, in the detector, this will be circles. So you go on changing. I think I should have a picture. Yeah. So now you see, if your angle theta is 0, that means particle is emitted along the beam direction. Your eta will be calculated to be infinity. Okay. So now you slowly go on changing your angle towards 90 degree, which is perpendicular to your beam axis, or from the interaction point. So what you will find is these are actually making on the detector plane, these make annular regions. Okay, so one eta to another eta, so those are making annular regions. For example, from the interaction point or in the detector, from the mid of the detector, or where your beam axis is going through, so from there, if you go to the boundary of the detector, essentially you are making different annular eta regions. Okay, so by that you are spanning the phase space, and the other way of spanning the phase space will be the phi, which you can define from this, from the position of the particle. So phi actually makes a sweep like this. So by this you make the eta phi space, which covers everything. And the advantage of eta I have told you, and I am going to show you a little more on this. So now if you are eta or y, whatever you take, so if you look into the y distribution, the rapidity distribution in the center of mass frame, it will be at 0. The mid of the y distribution will be 0. So this is the spectral shape, thanks to, I think, Nilkamal or someone actually gave me, I asked to help me with these plots. So if you look at the particle distribution in a center mass frame, I have plotted y star. Wherever I put a star, that corresponds to center mass frame. So you will find the mid of the center mass is now 0. And if I make a Lorentz boost, for example, if my center mass frame is moving with some velocity and I am sitting in my laboratory frame, so you will find the spectral shape is not changing. So that is the beauty for the experimentalist, that spectral shape is not changing. So what is changing is, you can find that if it is a symmetric collider, your y center of mass, I will show in my next class. So this will be half of ya plus yb, where ya is your projectiles. In fact, in the collider experiment, both are my projectiles. So ya and yb I'm writing separately, because sometimes your beam energies can be, or beam energies corresponding to the beam energies ya and yb could be different also. Okay, so so now you will find that your y beam, which is a y maximum, and that can be calculated using this formula. And when you make this Lorentz transformation going to the laboratory frame, so exactly this mid y or y center mass is shifted by this is exactly shifted by this amount of what you can calculate using your y beam. Okay, so making the spectral invariance of the particle. The spectral shape is completely invariant, and that is what actually the physicists are interested in. Compared to this, if you go on taking velocity distribution, since it is nonlinear, I do not know, I have not seen how the velocity distribution will look like. Maybe somebody can have a fun with that. And so now I took you to a position that eta phi are the right of variables in the relativistic domain to span our phase space to study the particle spectra. Okay, so is there any question so far? I know I may be going a little faster because of my engagements today. but I think these are more or less known to many of you. Okay, so what is important to note here is the shape invariance of the spectra, and I showed you, this is a simulation done by one of my students, I think Nilkamal also. So they did the simulation and they showed that spectral invariance is guaranteed in Y. Okay, so now I just rewrite just for out of fun. So if I rewrite all this beta, gamma, and I remind you that E is nothing but gamma m. So I will ask you little exciting questions before I migrate to center of mass frame and other related kinematics. Okay, so the question here is, let's say you are accelerating a charged particle from 0.1c to 0.2c. Essentially, it is 10% higher, right? So essentially 10% of the C to 20% of the C. So let's say this takes delta E amount of energy for you. Okay. And what about accelerating the same particle from same 10% difference, but at the higher end, for example, 80% of C to 90% of the C? Will it take the same energy delta E? What is the answer? Because the velocity is changing by 10%. This is the higher level. Anybody? Nobody wants to speak. Anyway, I cannot see anyone. So, any volunteer?
No, sir. It will not say.
It will not be same. Why? Your answer is correct. It will not be same, but why? Why do you think so?
If you calculate taking 0.1 C and the difference between the energy using this formula, then it will be different.
Why do we expect? Let's say I don't go to a calculation. Without doing calculation, can you imagine why this kind of things are expected, and what is the technological consequence of this?
Sir, actually, when you go to higher velocities, the mass of the particle is increased. So if the mass is increased, then you need more energy to accelerate it for a higher velocity.
Yeah. So essentially, to answer this question, I should have put the relativistic mass formula or the plot as a function of beta. So then you will see, once your velocity is going on increasing, the mass of the particle goes abruptly high, in the sense it's like this, and approaching asymptotically towards infinite when you are towards the velocity of light. So that means particle relativistic mass is becoming higher, and you need much higher in energy. So that is why it is not linear. So it is not directly proportional to delta E. Okay. Good. So then you go on thinking that why to dig million tons of earth to collide tiny particles. Essentially, we started colliding E plus E minus in left, and now it is P or heavy ions at the in the same tunnel at the Large Hadron Collider. So you should actually go on thinking, why such a big tunnel of 27 kilometers? What is the necessity, and what are the technological challenges, and so on and so forth. Okay. And for your information, in fact, you should be a little excited to know that CERN is planning to go for a 100-kilometer circumference FCC, okay, future circular collider ring, to increase the energy just by 7 to 10 times the present one. You see, 27 kilometers to 100 kilometers, and energy will increase by 7 to 10 times only. Okay, and will the beam particles reach velocity of light? What is the answer?
No, sir.
I cannot reach velocity of light, but still I am going with higher circumference and higher energies. What I am doing? Okay, so look into this technological challenges or whatever, why I cannot go to much higher in energy directly, what are the drawbacks, okay, and how much effort or time it has taken to come to this position. And I would say during your travel time, try to read a book written by one of the former Director Generals of CERN, Harwick Soffer. So that is actually The Lord of Collider Rings. So you can Google it. So that is a very good book, and that should be a travel time book for you. Okay. So you will know all about the efforts gone into making the Large Hadron Collider. Okay, and he was 2 times Sound Director General, and he has put up all his experiences of making Large Hadron Collider. Okay, so it is Lord of Collider Rings by Harwig Soper. So Google it and try to know more about that. Okay, so now let's migrate to a different topic. Okay, so now let's talk about center of mass or center of momentum and laboratory frame and particle motion in one frame and how we perceive different observables in another frame. Okay, so next 30 minutes, let's do that job and then we'll finish today's lecture. So now let's consider a Lorentz system, and I call it a laboratory system. Okay, because I know my definition of Lorentz system is it should be inertial frame, right? So both the frame of references should be related by a constant velocity, not acceleration, right? So these are 2 inertial frames. So now I say this is my laboratory frame, and in the laboratory frame, let me take 2 particles only for simplicity. Okay, and particles are identified with their masses like m1 and m2, and their 4 momenta is given p1 and p2. So let's assume that they are making an angle theta in between them. So P, the 4 vector of P1, I write E1, the 3rd vector I take P1, okay, arrow, and P2 is also written like E2 and P2. And so this nomenclature of writing, because when I do not put anything, any arrow, so that is my 4 vector. And again, you may be astonished, why I have no negative sign on the spatial coordinates. And I remind you that for covariant 4 vectors, I told you I will not put any negative sign. And whenever there is a, it is covariant should carry negative sign. But anyway, so I am just putting it like coordinates. My contravariant will not carry any negative sign. That was my metric. So each of the 2 momenta P1 and P2 may again stay or contribute to the total momentum of the system of particles, right? So if I say it's a system of particles, essentially system of particles total momenta will come from the individual energy and momenta of the particles. So what is the center of mass or momentum? Energy E. So usually you may see that always we say center of mass frame, right? So it is actually not center of mass frame. It is center of momentum frame. And just borrowing the word center of mass from our classical mechanics, we are using the same word center of mass. And keep in mind, although we go on saying it is center of mass, it is center of momentum. Okay. So what is the energy in center of mass? Because center of mass or momentum, you should perceive that it is center of momentum because your total momenta of the system in that frame of reference is 0. So that can only happen irrespective of the mass, that momentum should be opposite and equal to each other. So that is why the frame we are dealing with always by saying conventionally center of mass, it is center of momentum frame. So what is the energy in center of momentum frame? If you say center of mass frame also, nothing wrong. It is conventionally we are using it. But the right one is center of momentum. Fine. So it is independent of the Lorentz system in which P1 and P2 are defined. So that is what I'm saying. So if you look at the total energy of the center of mass, so it is actually independent of the Lorentz system, which is a laboratory system where I have defined P1 and P2. So it must be possible to get this answer in terms of different invariants. Because as you know, if we deal with invariants like the way we have dealt with your rapidity, which gave me spectral invariance. So if I deal with different invariants in relativistic domain, so my life will be easy both mathematically and also physics wise. So that is why in this problem of 2 particles, if you define the invariants in hand, whatever is available, I think you will be convinced or will agree with me that the invariants in hand are the following. First is P1 square, which is my M1 square, and P2 square is M2 square. And P1, P2 will also be invariant because this looks like a scalar 4-vector scalar product. And if you look at P1 plus P2 square, this will also be invariant. Similarly, P1 minus P2 will be also invariant. And I am not talking about any other things because I have only 2 particles P1 and P2 for simplicity. So these are the invariants in my disposal, and I am going to use them to have the expression for center of mass energy E. Okay, and keep in mind I will be always using star asterisk as the superscript when I talk about any variable in the center of mass frame. Good. So now if you look at, since I am in the center of mass frame, my P1 third vector or 3 vector plus P2 should be 0. So that is the definition of center of mass. So if I go on calculating what is my P1 plus P2 4 vector, this will be written in component wise as E1 star, E2 star, then spatial component is 0. So this I am writing component wise. So then what is my E star? So what is the total energy in the center of mass frame? This is nothing but E1 star plus E2 star, because the total momentum is 0. So I don't care about any other things. Okay. So now I write E star square. Always keep in mind that star refers to my center of mass frame. So E1 star plus E2 star whole square can be written as mathematically from this equation as P1. Okay. So this can be written as P1 star plus P2 star whole square, and that is nothing but your P1 plus P2 square, because this is giving me 0. Spatial component is giving me 0. No minus term there. Okay. And we also know that my P1 plus P2 square is Lorentz invariant, right? So then my E star square will also be Lorentz invariant. And earlier I wrote that P1 square or P1 plus P2 whole square will be again a mass square, right? So then let me define a mass M, capital M, which is the total mass of the system, and I name it as capital M square is equal to P1 plus P2 square, which is equal to the capital P square plus is equal to E star square. Okay. So if I rearrange the things, I will find that my E star square, which is E1 plus E2 square, so minus P1 plus P2 square is invariant. Okay, by definition. So now this invariant is essentially the invariant mass of the whole system, which is nothing but the E center of mass. So if I now translate the two particle system to a single particle center of mass, so now kinematically our two particles P1 and P2 are equivalent to one single particle with 4 momentum capital P and the mass capital M, which is equivalent to the E center of mass. That is what mathematically I am getting. Okay. So little more mathematics, but you see mathematics as a language of physics, we should enjoy it, and no big field theoretic calculations. So I think everybody should perceive what we are talking about. So furthermore, earlier we defined your third momentum should be gamma mv and your energy is gamma m. Gamma is defined in this way. Okay. And I can put beta, or I can also take out beta with v, assuming natural limit c is equal to 1. So now, I'm sorry. So now, hence the total momentum for momentum of the two particle system now can be written as capital P, capital E, and capital P by definition is my M. Here, look at here, M, beta, and gamma, and E will be your M gamma. So this M is nothing but the whole two particle system. It is the total mass of the system. So beta by definition is your momentum by energy. Okay. So if you put your momentum by energy, so this will be your P1, P2, because this is for momentum, and this energy is E1 plus E2. So this is the velocity of the center of mass seen from the laboratory, because now I am talking about this capital P's corresponding to the center of mass of the system. What is my gamma center of mass? What is the boost of the center of mass with related to the laboratory system? So that is again defined taking this beta center of mass, and this has to be E by M by definition. And once I put all these things together, I will find this is E1 plus E2 divided by E center of mass. So this is the Lorentz boost of the center of mass. So this gamma center of mass is nothing but sum of the energies of the particles in the laboratory system, which is E1 plus E2 divided by the energy of the center of mass. Okay. In principle, by definition, gamma is your E by M, and energy of the center of mass is equivalent to the invariant mass of the center of mass. So that is the reason your gamma center of mass is equal to the total energy available in the laboratory system divided by the energy of the center of mass. So this gives me at what boost factor or Lorentz factor my center of mass is moving. Okay. So I hope everybody is content, and these are the equations which are actually essential while dealing with different kind of particle kinematics. Okay, and whatever I showed you, I used all the invariants in hand. Okay, that was because of the necessity of Lorentz invariants of different quantities. So now if you look at the practical calculations, so we have to express all those things in terms of whatever things experiments give me. And if you see E1, E2, the emission angle cos theta, and P1, P2, all this third momenta. So these are actually the things which are given to me or I measured in experiments. Okay. So then I should go ahead to show that this E star square can be expressed just using the previous formulae. You can write that this is equal to m1 square plus m2 square plus 2 into E1, E2. So this E1, E2 are all the laboratory measured quantities, and m1, M2 are the two particle masses. And you will find that E star square is equal to this, and this minus will correspond to a parallel motion, and the plus sign will correspond to anti-parallel motion. Okay, so this is the master formula to calculate this E star square. Okay, and so I am not going to discuss, but I will give you 1 to 2 problems which you can take note of it, and these are actually direct problems in Hackathon, and it is conceptually more involved. So that is the reason actually I thought at least I refer to these problems and you can have a look at them. Okay. So the problem in hand is in the nuclei, the kinetic energy of bound nucleus goes up to the order of 20 MeV. Illustrate formula 1 and 2, which I have written here, by calculating the effect of this motion when it is parallel or anti-parallel to an incoming beam of 25 GeV kinetic energy protons, and you can take your mass as 1 GeV. So what is the difference in the center mass energy? What energies must be the incoming protons have to produce the same center mass energy? Okay, so all these things actually you can have a look, and this is more involved, and while solving this problem you should actually visualize what must be going on. Physical feeling is important. And the next problem is also equally important. I thought I should refer to you, and nowadays you can get these e-books and in your library these books, and try to solve this problem at least once to have a feeling. Okay, so now so let me go to the situation where I want to sit on one particle and measure the energy and momentum of the other particle. So meaning is, so in the frame of reference I am choosing, so I am sitting on one particle, meaning is, and the particle momentum is 0 to me, right? Because I am on the particle itself and looking into another particle. So this kind of situations may arise. So to answer this question, actually, you know, always it is always the same, no matter which Lorentz system you start with, because we have seen this thing in our earlier deliberations, and it must be therefore expressible by invariants, and the only invariants again in hand are the same things which I discussed. Okay, so these are, you know, in the two particle system. So I have all these invariants in hand. This is p1 square, which is equal to m1 square. You can show that taking your 4 vectors. P2 is square is equal to m2 square, and p1 p2 by definition scalar product of 4 vector is invariant, and p1 plus p2 square you can show later on that this is related to your Mandelstam S in a two-body system, and that is also Lorentz invariant, and this will be equivalent to your T variable Mandelstam T, so that is also Lorentz invariant. So that we are going to show slowly. Okay, so let now E21 is the energy of the particle E if we look at it in the rest system of 1. So energy of particle 2 when we looked it from the rest frame of 1 or the sitting on the particle 1. So now E21, let me write E2 for simplicity. So in the system where P1 is equal to 0. Okay, because I am sitting on that particle, so momentum, relative momentum looks to me 0. So now let's write that E21 in an invariant form. So if I write that, so now my P1, P2 will be E1, E2 minus p1 dot p2, right? So this is essentially I am making a scalar 4-vector product of p1 with p2. So then what I should do? So I should multiply the temporal components minus p1 dot p2, and minus sign is coming from one covariant, another contravariant. Okay, so in that way, so I can now write from this term will be 0 because my p1 is equal to 0. So I can write this is p1 mod, p2 mod, and cos theta, and p1 mod will give me 0. So that is the reason the second term is 0. And what is my first term? So first term, my E1 is equal to P1 square plus M square, M1 square. So P1 is 0. So that will give me E1 is M1. So my P1 multiplied by P2 is nothing but M1 E2. So I guess everybody can do this algebra, although I have written in a simple form. So what is my E21? So E21, I wrote it is E2, which is equal to now P12 divided by M1. So from this equation. Okay, and then as you can see, my energy is already in the invariant form because right hand side mass is invariant, P1 multiplied by P2 is also invariant. Okay, so now I can write what is my P21, the third vector. So this by definition of energy, so this is the definition. Then I plug in the values of E21 and put M1 and recalculate. So you will get that if my P1 and P2 are the four momenta or four momentum vectors of any two particles in any Lorentz system, then one can go on writing my E21 in terms of the invariants like this, P21 in terms of the invariants, all invariants like this, and similarly the velocity of the particle as seen from the other particle will be momentum by energy is your standard definition of velocity. So since these two are given now, you have calculated, you just divide this and you will get B21, and notice that this is also in invariant form. So always my aim is that I should rewrite as far as possible energy, momentum, velocity, everything in terms of the given invariant. Becomes the relative velocity. So these are the equations for E21, momentum P21 of the particle 2 seen from particle 1, because I'm sitting on the particle. Other guy or the other guy's velocity with respect to me, it does matter, and mathematically that is reflected with the symmetric nature, and you change 1 to 2, it does matter, as you can see here. I can make 2 1. Okay, and this is also a mathematical consistency which is coming in a natural way. So all these expressions are now invariants and can be evaluated in any Lorentz system. So once I am expressing energy, momentum, velocity all in invariant form, so I am independent of any Lorentz system. I am in laboratory frame or I am in center mass frame, it doesn't matter. Okay, so now I am giving you a new problem. So we calculated all this energy, momentum, velocity sitting on a particle and all that. So now this is a new problem. So can we calculate these things for center mass momentum of a particle? So this problem is now already solved, but there will be little resubstitutions because, as we know, the total momenta of the center mass frame is nothing but P1 plus P2, and we need to apply the previous formula with replacing P1 by capital P, okay, and P2 by the 4 momentum of the particle, which we are choosing to calculate. Quantities which you are looking for the particle. So then it is essentially a rewriting business, and I just go a little faster here. Okay. Yeah, so I have just done a rewriting business. So then the final formula are like this, and you will find all final mathematical equations are Lorentz-invariant equations. Okay. Fine. So these are essentially the mathematical expressions for what I discussed, and I can just quickly omit these things and leave it to you. Don't try to remember these things. You can actually calculate very easily once you understand how to write 4-vector and do the algebra. Remembering is not necessary. I don't recommend to remember this if you know the trick of the game. And in my next lecture tomorrow, when I calculate the threshold energy of a reaction, and that time you will realize if you follow the recipe completely, you don't need to be worried about these big mathematical equations, stars and arrows and other things. Okay, so let me omit this part and go to introduce briefly the Mandelstam variables. I have exactly 5 minutes, and let me take those 5 minutes to introduce Mandelstam variables. Okay, so in the interaction of two incoming particles, for example 1 and 2, I produce two final state particles, which is 3 and 4, and we can construct the following Lorentz invariants, which are called Mandelstam variables. And these Mandelstam variables have got more use in particle physics compared to heavy ion physics. So that is the reason for completeness sake, I should discuss these things. And in this two particle interaction 1 plus 2 going to 3 plus 4, I can define three variables which are Mandelstam S, T, and U. And those are defined in a way that this is your total momentum for momentum p₁ plus p₂ square. And this has to be by energy momentum conservation. This has to be p3 plus p4 square. Similarly, Mandelstam T is p1 minus p3 square. And if you realize if my particle 1 is also particle 3, so then this is the momentum transfer of particle 2 to particle 1. Okay, and then my particle 1 is essentially particle 3 in the final state, and this is nothing but the momentum transfer square. Okay, and this is also Lorentz invariant. So similarly, my U is p1 minus p4 square, that is also Lorentz invariant. In fact, given all these p1, p2s, you can construct S, T, and U. These are Lorentz invariant Mandelstam variables. So S is the square of the center of mass energy, and T is the 4 momentum transfer square. These two are more used. Essentially, S is more used by us. But in particle physics, when they look into S channel, T channel, and U channel interactions, so they deal with this kind of Mandelstam variables more compared to a heavy ion physicist like us. So we are restricted to more or less S and sometimes T. So one can actually show, taking the 4-vector algebra, which I did, that S plus T plus U is essentially the sum over of I, mi square. So all the masses occurring in the interaction, so that square is essentially equal to S plus T plus U. So actually you should go on showing this from starting from these equations. Okay. So if you see the definition of S, so the minimum value S can have is essentially your m1 plus m2 square. Okay, so that is the minimum value you can have. So because you will be involving two particles, particle 1 and particle 2, even if they are at rest, so they will give you the rest mass of the particle. That is why the minimum value S can carry is m1 plus m2 square. So since the definition of S is also on the right hand side p3 plus p4 square, the minimum value S can have to produce final state particles, because final state particles, unless they are produced, you do not have p3 plus p4. So that is why this should also be m3 plus m4 square. They are just produced like threshold production of particles. Hence, the minimum center mass energy required for a reaction to occur will be the maximum of this or this. Okay. So it could be shown that, okay, so this is just a note for you. You can actually work on this to realize that in order to produce, the minimum value S can have is m1 plus m2 square. For the final state particles to be produced, that will be m3 plus m4 square, because this is related to the threshold production of the particles, which I am going to discuss in my next class. And the minimum center of mass energy required for a reaction to occur should be maximized by this number, initial state m1 plus m2 square and m3 plus m4 square. So these actually, this algebra you can do and show by yourself. And it could also be shown that T is negative for any real processes. Okay. So when you talk about the T channel processes which are real, so the value of T, which is the momentum transfer, this has to be a negative quantity. So this also you can show, but as I discussed with you that I am not going to deal with these things in details, but rather I will try to take one example which we have discussed in one of our upcoming books, that find the center of mass energy A in terms of the Mandelstam variables and the particle masses. Okay, so if you have A plus B going to C plus D, so you express the center of mass energy of A in terms of the Mandelstam variables and the particle masses. And I urge you that try to solve this problem using 4 vectors, and I have given the solution here. Okay. And one more beautiful problem is if you look at the elastic scattering of identified particles like molar scattering. So molar scattering is discussed in many high energy particle physics books, which is E minus colliding with E minus, going to E minus and E minus. So you can show that Mandelstam variables becomes S is equal to this expression 4p square plus m square. T is also, T expression is this and U is this. And P is the center mass momentum of the incident particle, and theta is the scattering angle. So maybe you can try these problems, and if you face any problem, you can discuss with me. Next class will be a little tight because I have more materials to cover. In fact, 2 classes I have to cover in 1 class tomorrow. And if you have, we can set up a Zoom meeting separately sometime during the school or after the school. And if you have any problem related to this kinematics, I can take it up. Okay. So time constraint has to be respected. And certainly I cannot request Siddharth because of the tight schedule of the school that give me another class. But whatever necessary things I'll try to discuss leftover stuff tomorrow. And if there is any question while solving these problems, and you have any questions related to the classes, you can reach me over WhatsApp, we can set up a Zoom meeting, or you can write one email. I'll be happy to reply. In fact, I reply to emails immediately. Okay, so thank you very much. The solution is here, but you try to solve by yourself. Okay, so then I will migrate to my next lecture tomorrow.
Okay, thank you, Professor Sahoo. So if there is any immediate question, maybe Professor Sahoo is busy today, but
if anybody has, I can take up. Otherwise, I would prefer to take up questions tomorrow because of my tight schedule today.
Yeah. So maybe we can schedule the questions tomorrow. So,
yeah, or if you try to solve these things, if you face any problem, just feel free. We can set up a Zoom meeting and you share your screen and show me what is the problem you are facing, and I'll be happy to help you.
Okay, thank you, Professor Sahoo.